All right. Now I'm going to start with the circular motion. So I'm just going to take this as an example. I mean, it's something that you can easily do. Probably everybody has done. So you just tie something to a string and then swirl over your head, right? Whatever. So in any case, the quantities are given in here. So the mass is 0.1 kilograms. The length is 0.5 meters. And the frequency is given. So it's basically 3 rotations per second. So I would basically say that this is 3 hertz. I'm just inserting some typical numbers in here. Okay. So of course, we are going to assume that the string is perfectly horizontal. So as a result, this problem basically looks like this. So there's some kind of a center in here. And then I have some object tied to a string. Okay. The size of the object is negligible, so I'm going to assume that it has 0 size. It's a point particle. It just rotates around this thing in a circular track. So it's doing a uniform circular motion. Okay. In any case, so as a result of that, it has some certain speed in here. It also has some velocity. Velocity changes, so therefore there is an acceleration. I'm just going to show the acceleration with a blue color, but let's just show you with this one in here. Okay, so we also have the relationship of the acceleration to the speed is v squared divided by the length, by the radius of the circular motion. Okay, it's just a simple application of that, right? But there are some assumptions that we do in here. So we assume that well, this is essentially a 2-dimensional motion, and the string is there within that 2-dimension. Within that assumption, there's only a tension force acting on it. There's also a weight force, but that's irrelevant for the problem. Let's just forget about it. There's a tension force applied on it. As a result of that tension force, the object has an acceleration a, and so therefore the Newton's second law says that the tension is equal to mass times acceleration. Okay, so once I find the acceleration from the given information, I can then find the tension. Okay, let me just quickly do this. The speed is like 2 pi times the circumference. Sorry, 2 pi L, which is the circumference, divided by the period. Let's see, period in here. And the period is basically the 1 over the frequency. So as a result, I can write this thing down as like frequency in here. So as a result, the speed is like 2 times pi times whatever. This is 0.5. So let me write the times with a cross. And the frequency is 3. So that's basically this much meters per second, right? So this is the length traveled by the object within 1 second. And so as a result, this is what we get. This is about 9. This is about 9 meters per second. I'm essentially taking pi to be equal to 3. And so therefore the acceleration is v squared over L. So that's going to be 9 squared divided by 0.5. That's 160 meters per second squared. So therefore the tension is, I think the mass was 0.1 kilograms. So mass times the acceleration. So it's like 0.1 times 160. So that's going to be about 16 newtons. Again, let me say that this is approximately 16 newtons. Why did I solve this problem? Yeah.
Hocam,
Yes.
I think there is also a gravitational acceleration inside the screen, towards inside the screen. How come this does not affect on the object?
I'm going to solve that problem next, all right? So here we are making an approximation. We are making a simplification, right? So we will see that, well, that's okay. I mean, as long as you're accepting that you're just doing an approximate calculation, that's okay. But
Okay.
we can also take this into account as well. Okay, so the problem in here is that, I mean, this is the free body diagram. Free body diagram, which shows all the forces acting on the object. Acceleration is just optional. Some people usually draw the free body diagram like that. I mean, I know that, well, let me just write down the radius in here like that, okay, or mv squared over r. I know this from experience in the times where we had like the face-to-face exams. People usually solve the problem like this, and they somehow assume that the acceleration is equal to 0 or something like that. In any case, so they got the same relationship, but so as a result, the same solution, but there are some concepts wrong in here. So as a result, I'm going to say that don't use this. But there is one way of actually looking at this problem. It's basically looking at this problem from an accelerated reference frame. If you remember, I told you that you should not use accelerated reference frames because the laws of physics are different there. They are not expressed in the same way. So that's the reason why you shouldn't use them. But in any case, there are sometimes situations where you would also want to use these. But so for that reason, I'm going to talk about them. And when you use these kind of reference frames, it appears that the acceleration is 0, but somehow you also have to add some kind of a fictitious force like that. So the centrifugal force, whatever that is basically arises there, but it's not a real force, right? So just keep this in mind. So let me just say that, right? This is not a real force. Okay, so only the tension is real in here because it is the force applied by the atoms forming the string. So it's basically an interaction between two physical objects, the interaction between the string and the block in there. So that's a real force. Apart from that, there are no other forces in here. Well, there's also gravity as well, but we said that let's just forget about it, okay? Apart from that, these two, there's no such force in here. So as a result, I mean, if you don't know what you are doing, then let's just stick with what we already know. So why do we stress on this? Because we have to be very clear about the concepts that we use. Like the concepts that in this uniform circular motion, there's an acceleration in here, right? We didn't assume this. We didn't just guess that. We just deduce it from mathematics, right? We have taken the velocity as the vector velocity. It's a vector quantity. We have said that the velocity is changing in here. So the velocity vector is not constant. Velocity changes. So therefore, there has to be an acceleration in here. And we said that, well, it has to be perpendicular and whatever. Okay. So we have deduced the fact that this object is accelerating. So therefore, there has to be a net force on it. And moreover, the net force must be along the direction of the acceleration. So whatever, I mean, there has to be a net force in here. And it is obvious that since the string is pulling this object towards the center, this net force is provided by the string in here, okay? So I think the concepts are clear, but just remember the things that we have deduced before, right? It basically comes from all of these. And there's no such thing as like centrifugal force or anything like that in here, right? There's no such thing. I just keep this in mind. Okay. So I don't know if you have any questions in here. If not, then let's just solve this problem. I think I can only solve this problem. So that's basically a generalization of the previous problem. It's a generalization that, well, this angle is not close to 90 degrees. It can be anything, right? So sometimes people swirl this. So when you are holding this with your hand, you're also moving that point. But it is also possible to do the motion by just tying this to a fixed point. So that's basically what we are going to suppose, right? It's not an assumption, so I'm just going to look at that situation, okay? So that's a fixed point. So that's tied to a fixed point by a string. So the string has length L, okay? And then this is just given some kind of a motion so that it basically rotates in this horizontal plane in such a way that that angle is theta. You would like to find the period or whatever. I mean, you would like to find, for example, the speed and whatever. So by using, I mean, I can express everything in terms of the angle theta. Okay, so as a result, if I choose, for example, this angle theta to be close to 90 degrees, then probably we are going to get the previous results, right? So as a result, you can actually think of this as like this problem somehow contains the previous problem. But in the previous problem, we somehow made an approximation. Here, we don't do that approximation. Okay. So in here too, I mean, the object can be at different places at different times, but they are somewhat equivalent to each other. So as a result, I'm just going to consider only one location and only one location. By one location, I mean that particular location here where, yeah, whatever. I can think of this as within the plane, within the plane of the screen. Let me draw it like that. Okay, so I'm just going to draw the free body diagram like this. All right, that's where the block is. So that's where the center is. And somehow at the moment when the center and the block are on the same plane, then I draw this picture, okay? So the free body diagram is like this. There's this weight force. There's this tension force. Okay, I just draw the angles like that. Again, reminder, right? We don't write down the components of the weight force in here, like mg cosine theta and things like that, all right? Don't do these. Just show what the force is, right? Because, I mean, you may want to solve the problem from by using a different axis. Okay, in that special situation, the acceleration is towards the center, so therefore the acceleration is along that direction. The acceleration is related to the speed, so therefore, once I find the acceleration from this free body diagram, I can then relate it to the speed, okay? So I'm just going to solve the problem like that. I mean, yeah, let's just do it like this, okay? So in any case, so as a result, I'm just going to do it like that. So I'm going to choose the x-axis to be pointing leftward, y-axis pointing in the upward direction. And so I basically write down F equals ma along the x direction and along the y direction. Along the x direction, we have t sine theta is equal to mass times acceleration. Along the y direction, we have t cosine theta minus mg, and that's equal to 0. Okay, so from here, we find the tension to be equal to mg divided by cosine theta. So that's one of the questions. We have found the answer. Right? So somehow the vertical component of the tension cancels the weight force. There's a horizontal component of the tension, so I just inserted this thing in here. So that's basically, yeah, let me first write down the equation in here. So it's this first equation in here, so that equation. So therefore we find the acceleration, so that's g times tangent theta. Okay, so as a result, I can find what the acceleration is, and I know that the acceleration is related to the speed. So usually you think that you adjust the speed. And for example, by increasing the speed, you have to increase the angle somehow, right? So there's some kind of a relationship between the angle and the speed of the rotation. So let's just talk about the speed. So I know that yeah, it is this motion in here. I know that the radius in here is, that angle is theta, that's L times sine theta, right? I know that the acceleration is v squared over r. So therefore the speed is the square root of a times r. So therefore this is the square root of g tangent theta multiplied with L sine theta. All right, so the speed is, yeah, it's correct. So there's no problem with this. So it's the square root of g times L divided by cosine theta. And I somehow want to take the sine theta out. Okay. In any case, I mean, when you're swirling something, you somehow adjust the speed. But once you adjust the speed, you get the, you basically arrange that angle in here. So let's say it like this. Let's say high speed, that basically implies theta is close to 90 degrees. So the previous problem was about this, basically. So you can basically check this thing. For example, in that case, yeah, I'm just going to leave that to you. So you can basically check that the tension is almost equal to mv squared over r in that situation. But I'm just going to leave that to you. But in any case, let's just check that. Low speed also corresponds to theta being equal to 0 degrees. So when theta is equal to 0, this is 0 and that's 1. So therefore you get 0 speed. So that's the that's an almost vertical thing, right? This is kind of, I would say that this is like a usual pendulum limit. In any case, when you increase speed, the theta increases. When you have like theta close to 90 degrees, in that case, sine theta is close to 1, but cosine theta is close to 0, which means that the speed goes to infinity. So as a result, you can also situations where, I mean, when the speed goes to infinity, that angle approaches to 90 degrees. There's one last thing. I think that was the period. Yeah, the period. But since I have used the t as the quantity, so let me write down the period as like this. Okay, so the period is basically circumference divided by the speed, right? Let me just write it down like that, okay? Speed times the period, right? Basically, it's the distance traveled within one period is equal to the circumference. And from here, we then deduce the period. Right? This is 2 pi r divided by the speed. And I'm just going to write these equations in here. So the period is 2 pi times L sine theta, which is the radius. And then speed is this, the square root of g times L divided by cosine theta, and then sine theta. It is nice that the sine theta goes away. So therefore, the period is equal to 2 pi times square root of L over G times cosine theta. Okay. So I don't know if you have seen this. So we also have something called a pendulum. But pendulum doesn't do a circular motion; it just does the swinging motion. Let's say this is the swinging motion of pendulum. If you look at the period of the pendulum, let's say it like this: period of pendulum. That's a different motion. If you look at it, you get like 2 pi, that's approximately equal to 2 pi over. I don't know if you have seen this pendulum. Why it's pendulum? The period of the pendulum is approximately equal to this. So that basically happened. We usually we are going to look at the motion of the pendulum later. So that's in the last chapter, basically. It's basically this periodic swinging motion. We are also going to compute the period, but you might have seen this formula from somewhere else, perhaps, that the period of the pendulum is given by this expression. And it appears that this is very close to that expression in here, but that was a different motion. So this is the circular motion. In this case, there's no approximation in here. So that's, let's just show it like that, all right? That's the circular motion. So that's the circular motion. Okay. In both cases, there's the expression doesn't depend on the mass. It just depends on the length, the gravity, and the angle theta in here. Here, there's no dependence on angle theta. There's also no dependence on the mass. So the question is, I mean, these are quite similar to each other. Is this a coincidence? Especially if theta is close to 0. Yeah, I mean, when we look at the swinging motion of the pendulum, we basically look at these maximum angles to be close to 0, right? So only in that case, the period is equal to that, okay? So as a result, in that limit, so that cosine theta is equal to 1, so we basically get the same thing. Okay, so in any case, there are two possible answers to that question. So one is that, well, yeah, that's a coincidence, because there's a dimensional analysis thing. So if there is any kind of a time quantity and you just express it in terms of, let's say, L, M, and G, in that case, if you just express it as a function of these, in that case, there's just going to be just this expression that will appear and some kind of a constant that will appear in front, right? So as a result, this part is coincidence because dimensionally, this kind of an expression cannot be otherwise. And so as a result, we will always have the square root of L over G in here. So that part is coincidence. If you also have the theta as some kind of a variable in here, in that case, there's some kind of an arbitrary function of theta. I don't know how to write this function. I didn't want to use f. Let me just write f of theta in here. So some arbitrary function can enter in here, and that's what we observe in here. So it's like a non-trivial trigonometric function that appears in here. So in any case, most of the similarity between these two equations are because of the dimensional reasons. Because dimensionally, the formulas could not be otherwise. Okay, 2 pi, well, usually these kind of 2 pi factors actually appear in front of, especially when you compute the periods. That also can be explained. But somebody actually mentioned something in here. When we look at exact horizontal motion, it seems like pendulum, I guess. All right. Yeah, that's also true. Basically, this circular motion can actually be considered as this swinging motion plus that swinging motion, but there's some kind of an implication in here. I mean, if you just look at these components of the motions, let's say that this is the x direction, this is the x direction, that's the y direction, and that's the z direction, right? Think of it like that. If you just look at the x component of the motion or the y component of the motion, this looks like a pendulum motion actually. But we are going to verify this later, right? When we talk about the pendulum motion, I may forget about this. Please remind me so that we can go back to that problem and then I can actually show you the relevance of that in that chapter. So basically, you can then think of the circular motion as like these two swinging motions which are somehow combined with each other, okay? So as a result, you get some kind of a circular motion in that. So as a result, for small theta values, the two periods being the same is not a coincidence, actually, okay? There's some kind of a similarity in there, but at this point, it is too early to discuss this because there's some complicated mathematics in the way. And so as a result, I'm just going to leave it like that in here. All right. So this is another promise. I will talk about that thing, right, later, if I don't forget. In that way, I'm just like a politician. I always give promises, but I don't keep them all the time. So if you want me to keep them, then you have to remind me when time comes, okay? All right, I don't know if you have any other questions about this problem. Right, it's just a very simple application. Interestingly, I asked the same question in one of the homeworks. I think homework 4. Yeah, homework 4. But I don't know if you would realize this, right? I mean, it's not the same question. It's not the same physics. We don't have any strings in there, but the free body diagram is the same and whatever, the conclusions are the same. But the setup is a little bit different. Okay, let me just say it like that. In any case, so I won't be asking any dynamics question with circular motion because I said that, well, I won't, but I'm going to ask kinematics questions from circular motion. All right, just keep this in mind. Just remember this. It's not a contradiction in here. Okay, what else? Let's see which else questions I could ask now. Tomorrow I'm going to talk about friction. So perhaps I can solve the problems with friction tomorrow and next week. Yeah, I don't have much questions left without friction. So all the fun starts with the friction, I believe. I mean, there are these kind of questions like that, but like these, for example, like this is 37 degrees and that's 53 degrees. And then this is just rotating in here in this plane. It's just the previous problem, but there's one more string, for example. These kind of things, it's just moving by some certain speed. And then the question is like finding the tensions in here and whatever. I mean, so we won't, I'm not going to do this. So as a result, I'm going to leave early. Do we have any friction in midterm one? No, we don't have, unfortunately. But yeah, I said that I'm not going to ask any questions from chapter 5. Okay, but let me quickly say something about these, the frictions in here. I mean, there are various forms of friction actually, so we will talk about air friction later. Again, this is one of the promises, but it appears that I can deal with the air friction if I talk about the energy concepts first. And then we have this solid on solid friction. Okay. So the air friction is usually, let's say, can be thought as like the friction of an object moving inside a fluid. So you can also deal with the water friction, for example. If you are moving inside water, there will also be a similar kind of a friction. So let's say that this is like a friction when moving inside a fluid. A fluid is basically either a gas or liquid. Okay, so somehow the reason why there's a friction is that when you are moving inside a fluid, you just set some gas molecules or the liquid molecules in motion. And because of that, you lose energy. And that's the energy loss mechanism that is going to be responsible for the frictional force. And so as a result, I mean, this is the correct way of actually dealing with this friction. You have to first see the energy concept, then we will see this. Okay, so on solid, I mean, these are the questions that we are going to deal with in this chapter. So we will have these kind of situations in here. So even in this case, there are situations like, I mean, friction on a wet surface. Let's say this is wet in here, in which case there's some kind of a water film in here, water film. This is like the friction inside a fluid, perhaps, but I mean, there's some kind of a fluid layer between these two surfaces in here. And so as a result, I mean, there are also these kind of frictions as well. I believe that this is actually, this kind of a friction is best treated with this kind of a treatment. I don't know. I mean, mechanical engineers actually deal with these kind of frictions by themselves. Here in this chapter, in chapter 5, we are just going to see this solid on solid frictions. Okay, so that's first described by Amontons. But I'm not sure about the name now, spelling of the name. So if I made a mistake, I'll correct tomorrow. It's called the Amonton's laws of friction. Okay, they are empirical, meaning that he just observed the behavior of the objects, and then based on that behavior, he deduced these laws, right? So some of them are basically kind of against the common sense. So it basically tells us that the somehow the frictional laws, the frictional force does not depend on the area in here. So that's the contact area. So in any case, I'm going to talk about these tomorrow. That the frictional force doesn't depend on the contact area and whatever. So probably we are going to have a little bit better complete description of the these laws and the types of the frictional force tomorrow. Okay, so let's leave it here today. We will continue from that point tomorrow.